Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEM. The title for today's webinar is RFEM Webinar 2, Advanced Modeling. This is the second webinar of a three-part series where the first webinar we started off with the real basics of our program RFEM, such as the modeling, loading, and full analysis and design of our concrete and steel structure. Today we're going to focus on a few of the more advanced features in the program. So whether you're new to RFEM or you're already an existing user, hopefully we'll show you some features today that you didn't know existed that will help us in our overall modeling procedure. And then our third webinar will be next month and on BIM integration with Revit and Tekla. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Gerhard Rehm will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Tiefenbach, Germany office. If the control panel does seem to get in your way when you logged into this go-to webinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the webinar. You can do so within the same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So as far as the content for today's webinar, we will be utilizing the same structure that we used for webinar 1. And we're going through a series of different topics here, so utilizing that structure to show you how we can address some issues within the model, or maybe just to give us better results. The first, we will utilize our add-on module RF-STABILITY to show the different buckling behavior of our members and our overall structure. Then we want to address FEA singularity with concrete surface design. We'll explore line releases for a decoupled element action. We'll do this in a more global approach with a beam to slab interaction, but also with connection design as well, so on a much smaller level. I also want to show you result beams in the program and how we can use these for additional structure information after we have run our analysis. Then we'll take a look at the nonlinear material capabilities within RFEM with a plastic stress analysis of a steel connection. And lastly, we'll take a look at functional printing methods and printout report options. With that said, we can jump into the program. So the first thing I want to do is to pull up our model here, and this was the structure that we utilized in RFEM Webinar 1. So you'll hear me reference this quite often today, but in our Webinar 1, we started with a completely blank file, and we modeled this structure, loaded it, ran the analysis into design of steel and our concrete members. So if you are interested in that, because we won't be covering much of the modeling process today, feel free to log into our YouTube channel and search for Webinar 1 there, and you will see that introductory video. So I did make a couple changes as far as our webinar. I got rid of our third story over here. I changed around maybe a couple of the member section sizes just to be adapted to our presentation today, but overall, same type of concept with our concrete and steel structure. So previously we loaded the structure, and we ran our load combinations and got a full analysis. Now that isn't always the case. Sometimes we go to run an analysis after we have loaded our structure. And for example, we have loaded our structure with dead load here. Now previously everything ran great, but as we know with any finite element software that we're using, that doesn't always happen. So when we go to run this first load case here, as we know from RFEM Webinar 1, that this is running according to a linear analysis, we immediately get an instability. So instabilities are nothing new despite what program you're using, but I want to show you these features that make our lives a little bit easier within RFEM. So the first thing to know is the text about the specific quadratic instability. It says this model is unstable. The instability is found at FE node number 64, direction Z. So it immediately gives me a location and tells me that there's some type of issue in the global vertical direction. The model is statically indeterminate. So when I close out of this error message, you'll see that my big red arrows show me exactly where FE node number 64 occurs. Now, I'm not going to say that 100% of this time this big red arrow is going to point out our issue, but a lot of the times this really is where the issue is occurring. So when I scroll in here, I really don't see anything immediately. When I turn it to a wireframe model then, okay, well, I can zoom in here and see that I forgot to connect my node here of my beam to my transverse beam. Well, that's no problem at all. I can just easily drag and drop that to connect those two members. So you can imagine that when we have a huge model with a lot of members and we get this error message for an instability, that red arrow is a huge benefit to really narrow down on where that issue is occurring rather than it being a hunt, a needle in a haystack, trying to determine maybe if a node isn't connected someplace. So now we can go and run our load combination again, or this is our particular load case. We run it. Everything appears to run okay this time. We immediately get our deflections here, which we can decrease the deformation factor. So that's great, but now we need to run our first load combination, 1.4 dead load. So this is just a load combination from the ASCE7. I take a look at my applied loads. It's applying that 1.4 factor to all of my dead loads, our surface loads and line loads here. And maybe turning this back into the rendered view, I begin my first load combination analysis. And lo and behold, we get another error message. So it's another instability. But this time our text is a little bit different. It says our model is unstable and the instability is found at this location, direction X. So we have a little bit of a different direction that it's being affected now. But this says a specified load is greater than the critical load. So this tells me that at this particular location I probably have some type of issue with buckling because the specified load is greater than the critical load. Well, I can close out of this error message and zoom into this big red arrow here. Maybe I turn this into wireframe. I see that everything is connecting fine. So I don't really understand where this error message could be coming from. Well, this is where we can utilize our add-on module RF stability. So from our long list of add-on modules over here on the left in our project navigator, we can launch RF stability. As you can see, this is just a simple dialog box that pops up within the program, and it allows us to do an eigenvalue analysis for a few different eigenvalues based on the buckling behavior of our structure. And what we can do is to import different axial forces from either load cases or combinations. Now, because I was able to solve for my first load case dead load just fine, it makes sense to import in those axial loads to see how the structure is behaving based on those applied axial forces. Now, we have quite a few other settings here that I won't get into in too much detail, but we do have an option down here that I can calculate an eigenvector for an unstable model. So this is if I couldn't get the model to solve at all, so that the causes of the instability can be checked graphically. So this is a feature too if we couldn't even get our dead load to solve. Now for this, I will run the calculation and it quickly runs the different 4 eigenvalues. And I'll now see my results available in my tables here. So you'll see I'll have 2 different columns. The first is the critical load factor. Now the critical load factor is just a factor that I can multiply that applied dead load by before I'm going to see the associated buckling behavior. We have 4 different eigenvalues, so the critical load factors are listed here in ascending order. So probably our most important one would be this first eigenvalue. Now the magnification factor is just a relationship between the moments of a linear static analysis and a second order analysis. So essentially my first order moment times my magnification factor is going to give me my second order moment. But now we're a little bit more concerned with this critical load factor. So if I take a look at my graphics, and you can see we're still in this add-on module RF stability. We can see that with our drop-down box here, and I have my 4 different eigenvectors here. Well, looking at the first eigenvector, we can see the buckling behavior of this structure. And remember, I can only multiply my dead loads by 1.03 before I'm seeing this type of behavior. I take a look at the other eigenvectors, same type of behavior. It all has to do with these slender columns here. So you can imagine that when I multiply my dead load by 1.03, I see this buckling behavior. So when I'm trying to run 1.4 times my dead load, well, that's where our instability is coming from. These members simply can't handle the applied loads. So back under my data tab, and up at the very top is all of my input data. I can take a look at my cross sections, for example, maybe turn off my results here from RF stability. I click on my first cross section defined. It's a W6/9. That's a very small number. So perhaps I want to increase that to something a little bit larger. Well, I can just right click and edit all of these cross sections at once because they are assigned to a single cross section within the program. Open up my cross-section database, and here are all of my AISC shapes. So we would like to choose something more like a W10/49, much bigger than a 6/9. Still a 992 is okay, but obviously we're going to have a bigger cross-section here. So I click OK. It's asking me to clear my results. So now when we go to run our 1.4 dead load, run the analysis, everything should run fine because now we have a little bit more of a sturdier member there and we don't see that same buckling behavior. So you can see how RF stability is extremely useful, not even if you just have an instability, but if you want to see the different buckling modes of your structure. I did a few other webinars where I utilized RF stability to export as imperfections as well. Okay, so now that we have addressed instabilities, I'd like to move on to singularities. And the first thing to do is to turn off our results, and let's take a look at our top surface here of our concrete structure. So if I drag my selection toolbar or selection box over that top surface, I can use my drop-down box here to create a visibility by selected objects. Now you can always right-click and show the hidden objects in the background if you'd like, or you can right-click and turn that off so that we get a clean view of only our structure that we've selected. Under Views, I can create a new visibility, and we'll call this Top Slab. I click OK. So now I have this user-defined view under Views that I can always refer to despite whatever view I'm currently in. So this is the case when we go to show the hidden objects in the background and we show a wireframe view, that members are always 1D elements in a finite element software. Now our surfaces are 2D elements. But the problem is that where we intersect this column to the 2D surface, you can see here that the intersection occurs at this teeny tiny FE mesh element right here, the single node point. So we can imagine that all of our force transfer is occurring at this single point. So inevitably we're going to get very high stresses, very high forces. If we go to do design of this concrete slab, we're going to get high reinforcement simply because it's a product of the high internal forces at this location. Now in reality, when we render this, these columns are 15 inches by 15 inches, so we are going to get some load distribution. And like I said, this is not just for our program RFEM, this is common in any finite element software. So what tools do we have available in RFEM to help us address this so that we are not overly designing our structure? Well, the first, and what I'm going to do is to jump to a different model here that I have saved, and I have went ahead and used our add-on module RF concrete surfaces to do my reinforcement design. Now I have an entire hour-long webinar dedicated to just surface design using this add-on module, so we won't get into it today. But again, if you are interested in how we can do reinforcement design for this, refer to that YouTube video. So once we run our analysis in RF concrete surfaces to get design per the ACI, we have our different required reinforcement. The first is AS1 in the top direction. Now, judging by this red arrow, we can see the reinforcement direction, and you'll notice that where these columns are framing into the slab, we have high reinforcement given there. The same goes for AS2 in the other direction. Now, when we're looking at AS1 at the bottom, it's not the same, which makes sense. We have a lot of bending at the bottom of our slab between our columns, so that's where most of our bottom reinforcement is going to be. Same with AS2 at the bottom in the other direction. Now, focusing on AS1 top and for our slab with this particular reinforcement design. This is nice in terms of our contours, but perhaps we'd like to see this in a more numerical value. Well, we can do so with sections, and what we will do with our first section is up here in our dropdown, we can create a new section numerically. But before I do that, right next to it, we have the option to completely turn off our ISO lines. So these results will still be available, but I'm just simply turning off those ISO lines for the sake of making my section cut right down through the center of my slab. So a section is exactly what you would think of it. It's going to give me the internal forces or my results at that particular location. So we can create this section numerically. Now, the first thing I need to do is to give it a section name, section 1. It will be a section cut through my surface, and I can apply this to my single surface number 2 here by clicking on that graphically. The next thing to define is my start and end points for the section. So what I like to do is maybe turn on my drawing grid down here, and I can activate that down at the bottom, change my origin for my drawing grid, and I can choose my 2 points here by zooming in, and I want it right down that column line. So my second point will just be located at the second end of my slab, and because of those AutoCAD-like features, the program does a great job of just snapping to those points that I most likely would want to place my section. Now, the section on surface, the projection direction, we can have it in the global X, Y, or Z orientation, or we can define our own vector if we want it at some type of angle. Once I click OK, then it immediately brings me into the results diagram for my section, and you'll see our exact same results that we were viewing in RFEM, and in particular, we take a look at our reinforcement design per RF concrete surfaces. Here are those spikes in reinforcement where our columns are framing into our surface. I think we can easily say that this is being over-designed for those internal forces. Now, I can always exit out of here and view these surfaces, as you can see graphically on my surface as well. So going back to the results diagram by right-clicking, I want to show you guys a useful feature called smoothing ranges. So up at the top is the option to edit our smoothing ranges. Now, my first column occurs 3 feet from the edge of the slab. My second column occurs at 20 feet from the edge of the slab, and my third at 41 feet. So what I'd like to do is I'd like to smooth out the range, maybe 2 feet on either, or sorry, 1 foot on either side of the column for a 2-foot range there. So this is to account for the load distribution that's occurring when in reality the program's not accounting for that. So what we can do is define our different ranges. So for example, for our first column, the beginning will be 2 feet and the end will be 4 feet. The program automatically calculates the length as a total of 2 feet for that first smoothing range. The second will be from 19 feet to 21 feet. And lastly, for our third column, it will be from 40 to 42 feet. The program automatically assumes that we'd like to apply these smoothing ranges to what we're currently looking at, but we can always activate and deactivate different results available here. So now when I click OK, you can see the smoothing range applied. For example, column number 3, we went from 3.14 inches squared per foot to 1.65 inches squared per foot. So extremely useful in the sense that we can print this to our printout report. We can even use this drop-down box here and pull up one of our other load combinations. And for example, I'm going to clear out all of these result diagrams and just activate my MX and MY. Again, we're seeing those spikes in internal forces here. I can go back to my smoothing ranges and simply activate the checkbox for MX and MY for all 3 of these ranges. So now when I click OK, you're going to see the smoothing range applied here as well. Now, one thing to note, if we jump back to RF concrete surfaces, for example, the smoothing ranges are shown here, but if I were to exit out, they are not shown graphically here within the model. So the question is, well, that's great, but how can we apply this so that the program actually designs for those average forces rather than us just kind of putting a fictitious number after our results are shown in the smoothing ranges? And one thing I forgot to mention here, if we take this section cut and we highlight it, we hold down our control key, maybe we want to copy it down this other column line just to give us some perspective on some high design forces as well at this location. So smoothing ranges are great, but if we go back to our data tab, and we will see these sections available here. We have section 1 that we just created, and then here's our second copied section. There's another feature called average regions. So if I right click, I can create a new average region. Now for this, we want to apply it to a particular surface. So I graphically select surface number 2 here. And you'll notice that I have 3 different forms that I can select for my average region: a rectangle, a circle, or an ellipse. So for our particular case, our columns are rectangular in shape. So it's probably most beneficial to use a rectangular averaging region. But maybe you have a circular column framing into this slab. So that can be utilized as well. The next thing we want to do is to define where we want to apply the center of the averaging region. Well, we'll apply it to our first column here. The dimensions, if we want to average it out over a 2-foot section again, for both our A and B dimensions shown in this picture, we can. Now, you have a lot of control on what internal forces you exactly want to average. So the program assumes that for the local axes of our average region, U and V, we want to correlate those with the X and Y local axes of our surface. But in reality, we can activate all 4 of these if we just want to average out everything together, independent of what our local axes are doing, or if we're interested in maybe just averaging out our moments but not our shear and axial forces, we can individually apply those as well. For today, we will stick with the default, and I do want to apply this to each surface separately. Through all surfaces would be beneficial if we have a multi-story building here and we want to apply the same averaging throughout all the different levels. The internal force settings, you even have the ability to set all the result values over the entire region to 0. This might be beneficial if we're checking punching shear for a column and we're really interested in the shear at the critical shear section, and we don't want to design for anything within that critical shear section. So if we click OK, then we will get our first average region. Now, to make this very clear what we're doing, I'm going to jump to one of these particular load combinations, and under my results, I'm going to activate my sections. So we're still viewing our sections here, but for my MX forces. So this isn't my concrete design now, this is my internal forces MX. Now with this average region, all I have to do is to select it, hold down my control key, and then I can take it, drag it, and drop it. It's asking me to clear my results, that's fine, and drag and drop it to some other regions here. Now I can rerun that same load combination rather quickly here, and we will see that average region now apply. Now previously this was something like 83 kips per foot, so you can understand that this is now going to give us less internal forces. Now if we jump back to RF concrete surfaces, and it looks like we lost our results here, so I'm just going to quickly rerun that. And all this is doing is I went ahead and applied the ultimate limit state designs for all of my load combinations to do my reinforcement design. But what I want to show you with these average regions is that my AS1 top is still showing 3.16 inches squared per foot. So this average region did absolutely nothing to help us with that. So why is that? Well, back under the data tab, under Concrete Surfaces add-on module. So again, if you want a more detailed look into this particular add-on module, refer to our previously recorded webinar. But to let you know, when you are using average regions for concrete design, under the Details tab, it is default to have this option checked off. But what we'd like to do is to apply the average internal forces for our ultimate and serviceability limit state designs. So now we want to check this checkbox. I click OK, I click OK. We've lost our results again, but we can easily run a quick analysis, which you can see solves rather quickly, because now it's taking those averaging or those average internal forces to give us our reinforcement design. So now we have gone from 3.14 to 1.83. So this is how we can apply those average regions to address singularities within the program, especially for something like concrete design. Okay, so that is what I wanted to look at in terms of singularities. Now, switching topics, I'm going to cancel my visibility mode here, render my model. And in RFEM Webinar 1, if you can remember, if you were present, we created this beam member here, and it's actually a rib because we wanted to span from this column to this column, but we didn't have an intermediate column, so we thought it'd be best to apply a rib member there. Now, if I were to double click on this rib member, you can see that the member type is actually set to that. And previously we had defined effective widths for this rib member to take that into account for analysis, but also designed for our reinforcement per the ACI. Now, let's say we have a situation that we actually have a precast element, and the precast slab is sitting on this precast beam, and it's not a monolithic pour like what we'd see with a rib type member, but in reality, I want to fully release the moment. Maybe I still have resistance for my lateral movement and of course my vertical movement, so X, Y, and Z is fixed, but no moment will be transferred between the two. So what I'd like to do is to not have this set as a rib, but we'll set this to a beam member. Now when I click OK and it's asking me to clear my results, I take a look. Well, my typical member is modeled directly at the center line as the same center line as the slab. But in reality, what I'd like to do is to still drop this beam down below the surface. So how can I apply an eccentricity? Well, if I double click this member, we have a tab here called Options, and that's where you'll see member eccentricity. Now we need to define a new member eccentricity. And you'll see here that we have not only the local axis system X, Y, and Z for a member, we can also set it according to the global X, Y, and Z. The local might come in handy because if we are modeling a member at an angle, then obviously we want to apply the eccentricity according to the local axes rather than the global. Now we also can apply this movement of the beam in the X, Y, and Z, so not necessarily just vertical eccentricities, but left and right too. So typically with this situation, I would need to understand, well, what's half the depth of my slab, what's half the depth of my beam, add those together, and I can manually apply my eccentricity. But we have automatic features in the program that can do all of that for us. So you can see here that I have 6 different options of where I can select my beam to be, for the eccentricity to be applied to. This little red dot highlights on exactly which option I've selected here. So I'd like the top of my beam, and I want to offset it according to a surface. So then I can graphically select my surface number 2 here, and I want to offset it from the bottom of that slab. So now when I click OK through all these dialog boxes, we can see that that beam was dropped down below the bottom of the slab. Now this is the same concept as the rib member, but now we're not taking into account that effective width. One thing I'd like to do, and I created this user-defined view here of my top slab, and maybe we want to render it again. Well, what's going on behind the scenes, if we turn this into wireframe, is the program has dropped this member down below the slab depth, and it's applying little rigid links at every FE element along the member length. So the question is that these little rigid links have full fixity to transfer moment, shear, and axial forces, but remember, we're trying to alleviate these moment forces being transferred from the slab to the beam, causing high torsion within the beam. So how can we automatically do this without modeling modeling individually these little rigid links, what we may have to typically do. Well, in the program, we have a feature under data, and if I scroll up to my input data up here, you'll see a line release. So what I can do is I can right-click to apply a new line release. The first thing the program asks me to do is to define the line, and I will apply the line that I use to create the member. If I try and click the member itself, it doesn't allow me to do that because that's in reality not what the model was not where the member was modeled, but it was applied to this line integrated within the surface. Then we create a line release type. So with a line release, we have the ability to apply releases in the translation directions X, Y, and Z. You can see that we also have partial fixities here, so maybe we don't have a full release or a full connection here, but we can apply that partial fixity spring constant, and we can get into things like nonlinearities. Nonlinearities might be very important for something like friction. If we choose one of the friction options in here, then we have some different settings based on friction coefficients that will allow us to emulate that same connection type. Now, keep in mind that these are the local axes of the original line. So surfaces have their own local axes, our beam has its own local axes, and so do our lines. So we're not releasing any of the translation or rotation directions of the beams or surface, but rather the line itself. So we are going to completely release this rotational release, sigma x here, and we can click OK. We do need to define which is the released objects. Well, we will apply this to our surface number 2 again, and we're simply press OK, and we'll see the setting within the program that shows us that we have some type of line release here, judging by this blue symbol. So now if I were to run one of my applied load combinations, such as 1.2 dead, 1.6, well, we can run this load combination, and again, we're just viewing our initial view here, and I'm going to turn off my surfaces. And we just want to take a look at our member design. I'm going to turn off my sections. And rather, we're taking a look at our members and our internal forces for torsion. So you can see here that we still have a small amount of torsion along the member length of 1.933 kips per foot. But what would this look like had we not released that particular moment along the member length? Well, this is where we can jump back into the PowerPoint quickly. And I just put a couple diagrams side by side to show us the differences. So this is the internal forces, M sub T, so our torsion forces of this beam supporting the slab element, and this is comparison of when we release the moment versus when we don't release it along the member length. So without that line release, we're going to see that those torsion forces vary along the entire member length. At one point, we are at 12.315 kips per feet, and at the ends of our beams, we're clear up to 20.04 kips per foot. Now with this line release, you can see that nothing is occurring across the member length. It's just purely at the member start and the member end where we have a small torsion force of 1.91. So this is how we can effectively apply line releases in the program if, for example, we did not want to connect our surface to our beam element. Okay, so changing topics once again, I want to move on to result beams. For this, I am going to cancel out my visibility mode here. Let's render our model. And moving on to result beams. So let's say that I'm interested in only my concrete structure here. I'm not so interested in my steel structure, and in particular, I want to know what the story shear forces are. And again, I don't want to incorporate the steel beams, but just the concrete surfaces and members. So how do I easily pull that information from the program? And this is where something like a result beam will come in handy. So what I'm going to do is I'm first going to create a new user-defined view here, and using my drop-down box, visibility by selected objects. Now keep in mind that behind the scenes, when I show my hidden objects in the background, this steel section is still here. So under my views, I can create this new user-defined view. We'll call this one concrete structure only. I click OK. And I'm going to turn back on my grid. I'm going to redefine the origin at the base of my structure. I'm going to hold down my control key to select these two members, and once again holding down my control key, I'm going to copy these, drag and drop them to a location parallel to the concrete structure. So what I'd like to do from here is to select these two members, right-click to edit them. And under the member type is where we can choose result beam. Now, a result beam is simply going to take the information from other objects in the model and apply it so that we can view the analysis results as a member internal force. Now, result beams don't add to the stiffness of our structure. We're not applying them to an analysis. It's just simply a different way to view our results. So as far as a cross section, it doesn't matter if it's concrete, steel, aluminum, your own user-defined section, you can choose anything here. You'll also notice I don't even need to put a support at the base of this column section. What I need to do here is to define some additional information. Now, as far as result beams, we have 4 different options. The first is within a cuboid or quadratic. So this is going to use a quadratic integration area where the centroid of all of the elements that I'm trying to incorporate within this result beam needs to be located within the member's axis. And by member's axis, I mean the axes of our actual result beam shown here. So I'm not going to use this option today, but we will be using this second option as our second example today. So this is within a cuboid general. What this will do is it will apply a rectangular integration area where the centroid can vary according to the local axes of our member. The third option we have is within a cylinder, so this will use a circular integration area where the centroid must be located at the member's axis. And again, this kind of is clarified here with this nice picture that we have. The last object, or the last option here, is to choose from listed including objects. So here is where I'm going to start off with my first example of a result beam. And what I want to do is I want to select my surfaces that I'd like to apply to this result beam, so I can just highlight everything. Remember, my steel is in the background, but because it's not selected, I don't have to worry about selecting anything from there. As far as solids, we don't have any, but so we can leave this either as all or none. And members, we want to graphically select all of our concrete members here. I click OK. We can even exclude any objects from our selection if we'd like to here. I click OK, I click OK. Now I'm going to run one of our load combinations where I have a lateral load applied. So you can remember from webinar 1, we applied a wind load in the Y direction here with some gravity loads. So if I run this first load combination, then you will notice that after the result is complete, that I have my member over here with some results as well. So what's exactly happening? Well, I want to view my results on my members like I would any other member within the model. What this is doing is it's incorporating all of my objects here and it's applying it to my result beam just to summarize what's exactly going on. So as far as viewing my shear forces in the Y direction, and this is the local Y direction, so I can always right click and turn my local axes of my members on to understand exactly which direction I'm looking at here. The local Y is going to give us my story shear information. For example, the top story is going to be 10.46 kips for this particular load combination. My first story shear is going to be 39 minus the 10, and finally I have my base shear given here at 48 kips. If we take a look at our shear in the other direction, we hardly have any forces at all. That's just because we haven't applied any lateral loads to this. Now lastly, we can even take a look at our axial loads. So why would our axial loads be important? Well, if we're interested in our sum of our forces, I can see that for my concrete structure only, my sum of my forces in my Z direction is 1,455 kips. Now this is different from my table down here shown in my results summary, which we also give you the sum of the loads in the Z direction, but this is for the entire structure, including the steel structure over here. So again, results beam would be beneficial for only part of your structure here. Now, the moments are not applicable in this cases, and that is because we have moved the members of this result beam away from the centroid of our objects that we're interested in. So just keep that in mind when we're looking at something like moments. We can't get an accurate representation here. So I'll show you in just a minute how we can do so. But first, I want to quickly jump back to the PowerPoint here to explain what's going on. So as you saw with a result beam, we're integrating the results from a list of objects. Now, these result beams only include the elements within a rectangular axis of the member start and end. And a perfect example, this is a result beam shown here. So this is completely applicable to what we had just saw. And these fictitious turquoise planes here show you that the result beam's analysis and what we're seeing for those actual internal forces are only going to be defined within these two planes here, which are controlled by the member start, member end. So this red shaded portion here of our surface elements will not be included in the results, and that's just defined by the member start and member end. We can even model a result beam at an angle. You can model a result beam in every which way that you'd like, but again, you're going to exclude these red shaded portions purely because the boundaries will be controlled by those same planes at an angle as well. Now, as we just saw with the axial and shear forces, the parallel distance from the centroid does not matter. So going back to RFEM, I can move this result beam every which way in the left and right direction. But if you take a look at what happens when I simply move it in the vertical direction, those results are now gone. That's because I did not move it in a parallel direction to the objects that I'm interested in. So that's the one way that you need to make sure that you're able to see your results accurately for your structures, to make sure it is parallel. Going back to the PowerPoint, now our moments, which I just mentioned, torsion, strong and weak axis bending, the beam must be placed at the centroid. So let's move on to a quick second example then with our result beams of how we can utilize this to view our moments. For example, if I'm interested in my top slab here, which we can go back to our user-defined views, and I really want to design a 4-foot wide section here on my slab, and I want to pull those internal forces from that 4-foot wide section. Well, a section cut isn't going to work here because a section cut only gives me my internal forces at that exact location, exactly what it is, it's a cut. So in order to utilize a 4-foot section and to pull those internal forces, we want to use a result beam. So what we can do is to create a new beam member here, and instead of the member type beam, we will choose result beam. And again, the cross-section does not matter. We could choose anything that we like because we're not contributing to the stiffness of the structure in any way. We want to move on to the details of this result beam, and this time I want to choose within a cuboid. So if I'm interested in a 4-foot section, then that means I want to choose 2 feet on either side of my result beam, which is laid out quite clearly within this picture here. Now, as far as my vertical direction, this isn't as important because I don't have any members modeled above or below. I'm only interested in this slab, so 1 foot is more than enough to take that into account. But if I had any elements that were within this 2-foot vertical section, they would also be included in my results, so just keep that in mind. This list is no longer relevant because I'm using only this section up here. So when I click OK, and I can begin by modeling my new member, I will snap to the middle point of this line over here to make my result beam section right down the middle of this slab. You can see the program automatically snaps to the perpendicular section, just like what we'd see in AutoCAD. And here is my result beam. So we can see that 4-foot wide section. We can even render this if we'd like a little bit clearer view on what's exactly going on. So now when we take a look at our results, and I will run one of my load cases here, it doesn't matter, 1.2 dead, 1.6 live. I'm going to run the analysis. And what we'll see as far as our result beams, we can view them as we would any other member, as I mentioned before. So the first thing we want to do is take a look at our member internal forces, and perhaps we're interested in the moment. So let me turn this to wireframe view. Now, our moments have a nice smooth diagram for my beam member here. So what's going on with this results diagram? It's pretty choppy. Well, when you're using a result beam like this, under calculation parameters, we want to change the number of divisions of our members for result diagrams. The default is set to 10. Let's actually change this to something like 100. I click OK. My results will inevitably be cleared. I quickly run this analysis again, and we'll see that our results look much better. So that can impact the way that you're viewing your results. So you want to make sure and increase those numbers of sections here if you see any type of discontinuities that we saw with the beam before. So now we can see that our moment diagram is displayed quite nicely here for our strong axis. So remember, these are the internal forces for our 4-foot wide section, that we can take these internal forces and go and do our own design. We can take a look at the weak axis bending here. We can even take a look at axial and shear forces. These are all relevant within this particular section. But this is what I'm saying when you want to take a look at the internal forces of our moments, that the centroid of our elements that we're interested in must be at the same location as our result beam's axes. So just something to keep in mind there. Okay, so now that we have seen a little bit more about result beams and we have focused heavily on our concrete structure, let us cancel this visibility mode to take a look at our entire structure. And I'm going to render it. Maybe I'm interested in the steel structure, and in particular I zoom in here and I want to take a look at this connection here. Now this connection is pretty straightforward. We have members framing in at 90 degrees. But if we didn't, let's say we had tapered members, maybe we had members framing in at a weird angle, well, this might flag us to think, okay, well, perhaps we'd like to do a finite element stress analysis for this connection. But if I turn this into a wireframe view, I cannot do a stress analysis of this connection because all of my members are 1D elements. So we can get stresses along the member length and the member as a whole, but not for this connection. So what would we like to do about it? Well, the first thing to note is that this member, judging by this big red arrow shown here, the member end is framing into this node. The same with this member, but this third member, the member start is framing at that node. So what I can do is just right-click to reverse the member orientation. So now all three of my members will be framing in at this single node. I'm going to select them all, right-click, and I'm going to choose to divide the member by a certain distance. Now, because I switched around the member orientation, the member ends are all located at this particular node, so 3 feet from the member end is where I'm going to divide it. Now, I've done nothing more but just create smaller members out of my initial member length. Now, if I render this, sure, we get this rendered view of our W section, but turning it back into wireframe view, I'm going to highlight all three of these members. I'm going to right-click, and under member, I'm going to choose the option to generate surfaces from members. So now what we've done is we've taken these 1D member elements and we've turned them into 2D surface elements. So now this will allow us to do a stress analysis on this particular connection. Now, the first thing I want to do is under my display, I'm going to turn off my FE mesh refinements. I'll get into this later. So what we need to do, and first I wanted to mention that this W shape was previously a W 12 by 35. Well, this new W shape here generated by the surfaces has all those exact properties. For example, the web surface here has a thickness of 0.31. Well, that is taken from the W shape. All of my dimensions, my materials, my thicknesses were all taken from that member that was modeled previously, so I don't have to make any changes in regards to that. What I do need to do is to clean up the geometry a little bit before running my analysis. So I can highlight all of my members and I can create a new visibility by selected objects. Maybe I want to show my hidden objects in the background. Now, this is a nice little trick for even our users of RFEM who've been using the program for a while. If you didn't know, you can select one of these elements here, and if you hold down the Alt on the keyboard, well, then that will allow you to rotate about those selected elements. So just a nice little feature to utilize there. Now, to clean up the geometry, I'm going to start by deleting these center lines. They're no longer needed. And you'll see that the column is a little bit low here. So what I'd like to do is to extend this up a little bit above my beams here. So how I can do this is to zoom in here, and I'm going to hold down my control key to select the 6 nodes that comprise up the top of my column, and I'm going to use my move tool. Now I'm only going to move this 0.58 feet in the Z direction, so 7 inches in the Z direction. I click OK. So now you can see that the beam was just simply moved above those columns. Now the next thing is to move this beam here on our left to the face of the column. Well, that's pretty easy. If we rotate our model here, we zoom in, I can again select these 3 nodes that entail the top of this beam and just drag and drop them to the snap point of the face of that column. So again, those AutoCAD-like features will allow us to snap to the most important parts of the model. Again, I do the same thing for the bottom. I just simply snap to that point, and now I can see that that beam is framing in quite nicely to that column. If I take a look at my rendered view, we can see that here. Now notice the rendered view of our 1D elements transitions quite nicely to those 2D surface elements. But with that said, if I look at my wireframe view, these 1D member elements are framing into this 2D surface element again at a single FE mesh point. This is a singularity. Now, by no means do we want to use an average region here, because in reality what's happening is this whole load from this 1D member element should be distributed to the entire face of this beam. So how do we distribute that load? Well, that's where we can apply just our little rigid plate here at the end of our member. Now, under our surfaces in our drop-down box at the top here, we can choose something such as a polygon. Now, as far as the stiffness goes, I want to set this to rigid. So pretty high stiffness here, not infinite, but very, very high within the program. I click OK. So then I can draw in this little rigid beam at the end of my member, and now that load will be distributed as such. Now the same goes for my other beam locations. If I don't take care to draw in this little rigid plate, then I'm going to get singularity issues at all these other locations here. So I'm just snapping to the 4 points of my column. And if I render this, I can see that these plates are shown with the pink color here. That shows me it's a different material. Now, a couple other things to take care of before we're ready to run our analysis. Going back to wireframe view, and I take a look under Calculate, FE mesh settings, we will see here that the global FE mesh settings are set at 1 foot. Sure, 1 foot is great for our huge slab element of our concrete structure, but when we're looking at something as small as this connection, 1 foot is not ideal. So rather than changing this global setting, when I made that transition to these 2D surface elements, the program actually put in these FE mesh refinements for me. So that's denoted by this little symbol here. If I double click on it, I can see that the FE mesh was defined for each individual surface here with a target FE length of 1 inch. Now this is more beneficial because if I were to apply 1 inch to my global settings and I'm applying a 1 inch FE mesh to all my slab surfaces, my solve time is going to be much, much higher. So the more FE mesh elements you have, the longer it's going to take to solve. So it's in your best interest to utilize these FE mesh refinements for situations such as these where it requires a smaller mesh here but not anywhere else within the model. So now when I go to Calculate, Generate FE Mesh, and let me cancel out of my visibility mode here, we can see the FE Mesh is automatically generated. Everything ties together quite nicely. I don't have to manually submesh anything here. But when I look at my concrete surface over here, well, I can see that the FE Mesh is still 1 foot. So that looks great. Now, keep in mind, we can always apply our own FE mesh refinements. For example, maybe I have some critical points here where my beam is framing into my web, and I can hold down my control key to select 2 nodes. I can right-click to add an FE mesh refinement. So for this one, I create a new definition type, and we can see here that the node is automatically selected because the program knows that this is what we selected back in RFEM. We can give it a radius of 0 0.5 feet or 6 inches. Maybe our target length for the inner portion of the circle is 0.02, and the outer will transition back to that 1 inch of 0.08. I click OK. Now the program puts these symbols at those locations for my FE mesh refinement. I can go to Calculate, Generate FE mesh, and now we can see that the program has created this smaller mesh at this particular location, and it transitions nicely back into our surface mesh. Under the Display tab, we can always turn off these FE mesh refinement symbols. The FE mesh refinement is still there, but we just don't need to necessarily see those big symbols. So in regards to our connection type here, well, originally I modeled this structure so that it has a fully rigid connection of this beam here framing into this column's web. But maybe I go back and I decide, well, actually, I'm going to have some type of weld here, and this weld is not going to have a full moment transfer. So I want to relieve some of those moments within the beam framing into the column web here. So how do I apply that to this connection? Well, that's where we can utilize line releases again. So like I said, we're going to come back and apply line releases on a much smaller level here. So back under the Data tab, under Line Releases, we want to choose the option to assign a new line release graphically. So here, I don't want to override my previous line release type because this is my beam to slab connection that we talked about earlier. So what I'm going to do is I'm just going to simply create a new line release type number 2. I want to release this moment, but maybe, like I mentioned, we have some type of partial fixity here with the weld type that we're using. So it might be something more like 40 kips per foot for partial fixity. So I can click OK. The surfaces that I'd like to release these lines from, I select my web element. I click OK. So now when I exit out of this dialog box, I can graphically select these lines of where this beam is framing into this web. So now you can see my symbols showing my line release here, and of course under the display we can also turn those off as well if we don't like to see them. So we're almost ready to run our analysis, but let's take one final look at our applied loads, and we will jump to our dead load here, see our applied loads. Now these are member loads applied in kips per foot along our various steel members here, but we no longer have members, so we lost those applied loads. Well, in a similar sense, we can apply the same load magnitude, but this time as a new line load. So line loads are applicable for something like a surface, for example, where we don't have a member available. We apply it in the global Z direction with a magnitude of -1.1 kips per foot. I can scroll in here, apply that to the top of this beam, and you can see it transitions quite nicely from our beam to our surface element. Now the same thing can be done for our live load. We'll apply a new line load here, but this time we want to give it a new load magnitude of 0.3 kips per foot. I click OK, and then I can apply that to the top of this beam. So now we can run our first load combination. So here I'll just apply the 1.2 dead plus 1.6 live. We can run our analysis. Now keep in mind this will take just a split second longer because we've now introduced these new finite elements for this connection into the program. As you can see, it still solves rather quick. We can turn off our loads, and I'm going to actually choose a user-defined section here. Visibility by selected objects. Now under my results, I'm probably most interested not in my members, but this time I'm interested in my surfaces. And under surfaces, we have our von Mises stresses. So now when I'm taking a look at this particular connection and my von Mises stresses, maybe I select my point here to rotate about that, I have some pretty high stresses here at these critical points. As you can see, 165 KSI. Now you'll notice that the program is smoothing all of these internal forces together, and that's just so that we can have a nice pretty picture of what's going on with our connection. But in reality, this isn't a correct way to view our results. So this is so important with any finite element software that we pay careful attention to how we're viewing these results, such as stresses on our surface elements. Now again, with my AISC Advanced Steel Design webinar, I did an entire hour dedicated to a connection just like this, and I go into much more detail, but obviously we're almost out of time today. So the only thing I want to show you is that rather than tying it together with this smoothing algorithm, we'd rather view our results here under our display tab in our project navigator. Under surfaces, the distribution of internal forces and stresses, we'll view this as constant on elements. So now each particular FE element has its own contour, and we're not trying to tie those together, and our stresses went down from 160 to 121. They're still high, but you can see what a difference that makes. So now that we still have extremely high stresses, I think we're all in agreement that this is much beyond the yield strength that this connection type can handle. So maybe real quickly, we'd like to utilize the nonlinear capabilities within the program, such as a plastic design. So what I can do is I can select all of my surfaces here, and I can right-click to edit them. And currently, I'm just using the Steel A992 defined within the program. That's what all my Steel members are designed for right now. But I'm going to create a new material. And again, I'm just going to go to my material database, and we covered all of this in webinar 1. And I'm going to activate my favorites group to select Steel A992 here. So I still want all those same properties, but my material model I'm going to choose is isotropic plastic 2D 3D. So for this, this allows us to do a plastic analysis within the program. Now we can get into some very complicated details here, such as things like tearing, yielding. We can change our strain hardening modulus, but for this example, you can see that our yield strength is more or less set to 50 KSI, and our strain hardening modulus is given as such. I click OK through these dialog boxes, so now I've just simply changed those surface elements to utilize the isotropic plastic 2D, but all the rest of my steel elements are still utilizing an isotropic linear elastic material model. So now when I go to run this exact same load combination, what the program is going to do is apply these loads to each element within this finite element connection, and the minute that it reaches the yield strength of 50 KSI, that load is distributed to the adjacent FE mesh elements. It will continue to do so until the elements have, or it will continue to do so until the load has been fully distributed. So in reality, we shouldn't see a single FE mesh element here higher than 50 KSI. And taking a look at our stresses, that's exactly what's occurring. The highest stress here is 50 KSI before that load is distributed to an adjacent element. We can also now view under our results tab, because we're running a plastic analysis, you'll see an option for criteria here. Criteria shows us our nonlinearity rate of our single element, so you can see exactly which elements are in the fully plastic state or have completely yielded. So just a little interesting topic, and like I said, my advanced steel design really goes into much more detail on this if you are interested in something like this connection. So one more quick topic to cover before ending this webinar is just a couple printout report options. The first, which maybe some people didn't know existed who have been using RFEM, is a 3D PDF. So for example, let's say I'm interested in quickly printing off this connection details to a 3D PDF. Well, I can either go to File, Print Graphic, but we also have a quick tool here under our toolbar called Print Graphic. And we can print directly to a printer, we can print to our printout report, but we also have the option to print to a 3D PDF. So when I click OK, it just asks me to simply save it. I can save it wherever I'd like. And then it will automatically launch this 3D PDF based on my structure here. So when we take a look at this 3D PDF, here's our entire structure, and what's great about this is that now we can make changes on our view within the actual PDF Adobe program here. We can spin it, for example, to take a look at our connection here. We can use the pan tool to zoom in and to really focus on this connection in particular. So again, you can see how this can be beneficial for any type of graphic views for a 3D printout. And then we can email, we can add this to a printout report, we can do whatever we'd like with it. Now, the other quick topic to discuss is if we are interested in our results and quickly printing off many load combinations at once. So for this, I'm going to jump to an already saved model, just back to our concrete example here of our slab. So let's say, for instance, that I'm currently taking a look at my MX forces here of my structure, and I want to take a look at all of the different load combinations, and I'd like to print this off directly to my printout report. So typically I'd have to take a picture of my load combination 7 here, add it to my printout report, change my load combination, take my picture of load combination 8, add it to the printout report. So what features do we have that make our lives a little bit easier? Well, under the print graphic report again, we have this option here called mass print. So I am going to print to our printout report, and I'm going to use the full page width, but maybe I want to use 50% of the height to get a couple pictures on each page. Well, under mass print, this is where all of our model data, our loading data, and our results data is available. This is basically exactly what we're seeing in our results project navigator. Now, the program's assuming that we'd like to print off what we're currently viewing. So you can see it's showing me MX for my surfaces. And instead of the current load case and combination, I want to print off all load cases and combinations. I click OK, I click OK. So now the program asks me to generate my printout report. Well, I can maybe select one of the saved templates I have. I click OK. So now the program is cycling through all of the different load combinations for my particular MX internal forces of my slab, and it's going to automatically add them to my printout report. So now you can see that we jump directly to where those pictures are added. And I can zoom in here to show you guys exactly what's going on. So here's my load case 1 dead load and my applicable MX forces. Load case 2, we can get into our load combinations 1, load combination 2, and so forth. So you can see how this can be extremely valuable if we're trying to quickly print off a lot of different load cases at once or results. We can automatically do that. Now keep in mind, you can always right click to edit one of these pictures. If, for example, I don't want to see the FE mesh settings, well, I can go under my display, scroll down to my FE mesh, turn that off, I click back, and now you'll see that that picture that I currently edited is automatically updated to not show the FE mesh. Now, something other very powerful feature, if I make any changes to this model, including maybe different loads, different cross sections, all of these pictures will update automatically. So I never have to worry about reprinting all of these pictures. I think our printout report is one of the more strong features of our program, especially in comparison to maybe what you're currently using. You can always add your company logo, your company header. You'll see all of the add-on modules are added to the printout report as well. And if we wanted to switch the order of these, for example, remember running RF stability at the beginning of the webinar. If we maybe wanted to have RF stability in our printout report before our design of our RF concrete surfaces, all I have to do is to select it and drag and drop it, and the program will automatically update the printout report to put RF stability before RF concrete surfaces. So again, just a very powerful feature in terms of our printout report. So with that said, we can jump back to the PowerPoint to conclude our webinar today. I know that I flew through this information, so if you are interested in any additional add-on modules or RFEM itself, we certainly have much more available on our website at Dlubal.com. This webinar today will be recorded and put on our YouTube channel, so you can always reference to it, because again, I know I went rather quickly, but perhaps you saw some things today that you'd like to revisit. You also heard me say that we have a lot of previously recorded webinars also available on that YouTube channel. Now, if you have any questions, in regards to today's webinar or anything else, feel free to send me an email at info-us@dlubal.com. And our phone number here in Philadelphia is 267-702-2815. We will have many more upcoming webinars. I try and do them about once a month. As I mentioned at the beginning of the webinar, our third and final webinar of this three-part series will occur June 14th, so next month, and it will be integration into BIM workflows, so utilizing Revit and Tekla and how we can integrate that with RFEM. You can register at Dlubal.com under support and learning webinars, and as most of you know today, I always send out a couple email reminders when those are coming up as well. So many of you would like PDH credit for today's presentation. That's no problem at all. The one thing that I do request is that you send me an email to info-us@dlubal.com and let me know who was in attendance for today's presentation, and then I can individually issue those certificates for you. So again, please send me an email at info-us@dlubal, that's DLUBAL.com. And with that said, I want to thank everyone for attending today, and as always, we hope to see you at our next webinar. Thank you.